All right, let's review a bit about where we were when we last got together and we did our calorimetry. Let's go through the calculations on determining the change in enthalpy using that. Um, let's have a look at that. So um, in our situation, because pressure is constant, we can say that the energy released in the reaction is going to be the same thing as the change in enthalpies. So for constant pressure situations, that's true. So we're rewriting the familiar equation of Q equals mc delta T. We're rewriting that as delta H, change in enthalpy, equals that. Now, all of these variables are given except for the one that we had to determine whenever we put the thermometer in the calorimeter. The specific heat of water is the same thing. We're going to use that. The mass is going to be 200 grams because we're going to have 100 grams of 1 molar sodium hydroxide as well as 100 grams of 1 molar hydrochloric acid. And so all we have to do is figure the delta T. Now, when I ran through this, my change in temperature was 7.75 degrees Celsius. So let me show you how I solved my equation. Okay, so we're looking for the change in enthalpy, and we're going to use the mass of the solution, the specific heat of water, as well as the change in temperature. So my change in enthalpy is going to be equal to 200.0 grams. I got that because I have 100 grams of sodium hydroxide and 100 grams of water. I just add those two together. Times the specific heat of water, 4.184. And my delta T was going to be, when I calculated it, was 7.75 degrees C. 7.75 degrees C. So I'm going to multiply those through and come up with an answer. Okay, and when I multiply that out, I get negative. It releases energy, so my sign is going to be negative. 6,485.2 joules. Of course, I only have three significant figures here, so I'm going to adjust that, and I'm going to say that I have a negative 6,490 joules, and I can convert that to kilojoules because eventually I'm going to need that in kilojoules anyway, so I'm going to say that's going to be equal to negative 6.490 kilojoules. There we go. And that is how we determine the change in enthalpy using a calorimeter. All right, the next way we determine the change in enthalpy is we use the bond energies. Now, the bond energies, one thing you want to notice is that there's no issue about phases. It doesn't say anything about solid, liquid, or gas, and it will say something about solid, liquid, or gas whenever we talk about the delta H as a formation. But for here, these are just straight bonds that we're looking for. The key thing that you need to be able to do is to be able to read the equation here and know that this is a carbon-hydrogen single bond, like that, and you need to know the formula for oxygen, that oxygen is homonuclear diatomic, but oxygen is a double bond. It's not a single bond. You need to know that these carbon-oxygen bonds are double bonds also. So for example, in this molecule, you're going to have two bonds that are these two carbon-oxygen bonds right there. And then the water, these are going to be single bonds between your oxygen and your hydrogens, and so they would be the same here. So I'll walk you through how to do just this one example, and then we'll move on after that. So here's our formula. The change in enthalpy is going to be equal to the sum. That means we're going to add up everything that's within these brackets. That's what that sigma means, the sum of the energy required to break the bonds of the reactants. And so these are going to be the reactants. And we're going to subtract from that the sum of the energies released when the bonds are formed, the products. And so here I've just rewritten the equation. The change in enthalpy is equal to sum, that's that Greek capital sigma, the energy required to break the bonds in the reactants, subtracted from the sum of the energy for forming the bonds of the products. And here we have our chemical reaction here, our equation. Methane, that's what CH4 is. Oxygen, carbon dioxide, and water. And like I said, you need to know the structure of these in order to know the bond energies. So to know the structure, we're just going to say that we have carbon and it's got 4 hydrogens around it, like that. And we have 1, 2, 3, 4 carbon-hydrogen bonds that we need to account for this. So I'm going to say 4 times, and then we're just going to go back to that chart and see where our carbon-hydrogen is. 4 times 411. Okay, so that's for our C4 bonds. And now we got to do our oxygen bonds. And so I'm going to say plus. I have 2 of these guys, and you need to know that oxygen is like so. So I'm going to add up 2 of those oxygen double bonds, and my oxygen double bonds are right there, 494 kilojoules per mole. So that will give me now the energy required to break those 2 bonds, and now I'm going to subtract from them the energy required to form the bonds. And there's a variety of ways to write that, but I'll just go ahead and put big brackets around here like this and show that I'm going to subtract from that figure the energy required to form the bonds. And over here, I need to show that my carbon dioxide is a molecule like that, and my waters are very familiar to you at this point. 2 of those. There we go. So I have 2 of these carbon oxygen double bonds. So I'm going to say 2 there, and then I got to go back to that chart and find my carbon oxygen double bonds. Those are 799 kilojoules per mole. And it's because it's the sum of these, I'm adding these together and I'm adding these together. And then I'm looking for these oxygen hydrogen bonds, and I have 4 of those. 1, 2, 3, 4 of those. So 4 times, and then go back to my chart again and find my oxygen 459 kilojoules per mole, and then do a little bit of math. Okay, so I'll just add up my numbers. I get 4 times 411, I get 1644. 2 times 494, I get 988. I'm going to add those 2 together, and I come up with 2,632. And then I'm going to go back over here. 2 times 797, I get 1598. 4 times 459, I get 1836. Add those 2 numbers together, I come up with 3434. Subtract 3434 from 2632, and I come up with 802 joules per mole. And it's a negative number, which is what we would expect because this is a combustion reaction, and combustion reactions liberate heat, and so that's how we work through that. Okay, and this is where we ran into some trouble last time when we did this, so let's walk through this as well. So the change in enthalpy we can calculate it because enthalpy is a state function. In other words, it doesn't matter which reaction took place to form a product, that you always require the same amount of energy to form that product regardless of the path you took. That's what we mean by it's a state function. And so Hess's law states it this way. It says the total enthalpy change for a reaction doesn't depend on the path, only the initial and the final states. So if we know what the initial state is and the final state, if we know what the reactants are and the products, then we can calculate that. So here are a list of enthalpies of formation for certain compounds, and I'll show you a chart. Well, let me just scroll to that all the way to the bottom. Usually when you see these charts, they are charts that look like this, and they don't just have the enthalpies of formation on them, but they have the change in Gibbs free energy as well as the entropies, so you can look up on one chart all the data that you need. But I'm just simplifying it here in this case because I just want you to focus on the enthalpies of formation. So our formula says this, that the change in enthalpy is going to be equal to the sum. So we're going to add up the enthalpies of formation of the products minus the sum of the enthalpy of formation of the reactants. And we are holding the constant, the pressure constant. So in that case, the heat generated is the same thing as the change in enthalpy. And so a couple things you need to note about calculating change in enthalpies when we're dealing with enthalpies of formation is that they always occur at a certain temperature, and so that's 25 degrees Celsius. So you can't use these numbers if you're at a different temperature, and they are the they occur at 1 atmosphere pressure, which is basically what we have, on the surface of the Earth. It's, it varies a little bit, but not a whole lot. So the other thing to notice is that we subtract the change in enthalpies of the reactants from the products, as opposed to when we were talking about up here, we were taking these are really the products over here, and we were subtracting the bond energies from the reactants. So you have to remember that when you're doing the change in enthalpies of formation, these two factors, they kind of switch on you. So pay attention to that. All right, let's calculate the change in enthalpy based on the enthalpies of formation for our calorimetry experiment. So we're keeping everything the same that we had. You're still going to have your 100 mils of 1 molar hydrochloric acid, and you're going to neutralize it with 100 mils of 1 molar sodium hydroxide, and you're going to form sodium chloride and water. And we want to know what is the change in enthalpy for that reaction. Well, let's have a look at that. So here is our equation. Change in enthalpy is going to be equal to sum, that's that capital Greek letter sigma, and the lowercase n means the number of moles of the P, the products, and we're going to sum up the delta H's of formation of all the products and subtract from them the delta H's of formation of all the reactants. Now, if you're like me, the most difficult thing about doing any of these is keeping my negative signs straight, because my delta H's of formation are going to have negative values, and I'm adding negative values together, and then I'm subtracting another set of negative values. And so you have to keep track of the sign of your equation. So let's walk through this. Really quickly, we'll just write out the formula. So HCl in the aqueous plus sodium hydroxide in the aqueous is going to go to sodium chloride in the aqueous, and then liquid water are our products that are associated with that. When I start to write my equation, I need to remember that it's going to be these products that are going to go there, and it's going to be these reactants that are going to fit into that equation. All right. The other variable that we need to insert here is our value for N. What's the number of moles of our hydrogen chloride and our sodium hydroxide? And this is how we calculate the number of moles. This should be fairly familiar to you. To calculate the number of moles, you need to know the concentration of our initial solution. So we had 100 milliliters of 1 molar sodium hydroxide and 100 milliliters of 1 molar hydrogen chloride. And so 100 milliliters, if I know that I have 1 mole per liter, like 1 molar sodium hydroxide, 1 mole per liter, if I have 100 mils of it, that's going to be a tenth of the number of moles. Another way to do that is to write it out this way: 100 mils. I got to convert my mils to liters, so there are 1,000 mils in a liter, and now I know that my concentration was 1 mole per liter, so I can cancel out my liters, cancel out my mils, and I'm left with how many moles are there in 100 mils of a 1 molar solution? And the answer to that is 0.1 moles. And the good news for our reaction here is that everything is going to be 0.1 moles. Our hydrogen chloride is going to be 0.1 moles, our sodium hydroxide, as well as our products, sodium chloride and water, because they all exist in a 1 to 1 to 1 to 1 ratio. So that simplifies the way we can write our equation to solve our problem. Okay, so when I write this out, I have the sum of my products. The delta H is a formation of my products. And where I get this number, negative 407.27, is I have my products, sodium chloride and water. So I'm just going to go look at the chart that we were looking at earlier. Sodium chloride is negative, let's see, oh, excuse me, sodium chloride, there we go, minus 407.27. And my liquid water is right there, minus 285.5. I wrote down 285.8. I must have found that on a different chart. We'll keep going with this. And so I'm going to add those two numbers together. And once I say the tricky part of all this is just keeping track of these crazy negatives. So this is a negative 407.27 plus a negative 285.8, and then multiply that by 0.1. And when I do that, I come up with a negative 69.307. And now here, this is the sum of the number of moles of my reactants. And so I'm going to look for my hydrochloric acid and my value for sodium hydroxide and plug them in here. And once again, we take those right off of our chart. So our hydrochloric acid is negative 167.2, and our sodium hydroxide is negative 496.15. Plug those numbers into our equation, and what we end up with is negative 63.635. So once again, keeping all of these pluses and minuses together and right, negative 69.307 minus a negative here. So anytime you subtract a negative, you can change both of those signs to positive. So a negative 69.307 plus 63.635 is going to give you a negative 5.67 kilojoules. Now, if I compare that value with the actual value that I determine in calorimetry, I mean, they're not exactly the same. My calorimetry value came up to 6.48 kilojoules. I actually remember I reported it in, I said 6.48 times 10 to the third joules. Well, that's the same thing as 6.48 kilojoules. And so negative 6.48 is not the same thing as negative 5.6. But given our simple cups that we're using and the system, there's a difference, but we are still in the same ballpark for the change in enthalpy as a result of this reaction. All right, so let's look at another example. Once again, we are going to be using the change in enthalpies of formation to solve these problems, and we're just going to look up those values in some chart that we find, whether they're in the back of the textbook or just a chart that we carry in our notebook. The interesting thing that we add to this one is, so we're not going to talk about 1 mole. We're going to start with the number of grams. And so in order to solve our problem, we're going to have to move from grams of iron to moles of iron. But other than that, this is going to work the same exact way that our previous problem worked. And I'll show you how we work through that. So the first thing you have to do is to be able to write out an equation. So I tell you that you're going to have 223 grams of iron. It's going to react with excess oxygen to produce iron oxide. And we want to know what the change in enthalpy is. So if we write out that equation and balance that equation, that's going to help us. So it takes 4 iron, and those are solids, 3 oxygens, and those are going to be gases, and 2 irons are formed in our product, and 3 oxygens are there. So we're going to look up the delta enthalpies of formation of our products and subtract from that the delta H is a formation of our reactants and solve the problem. And the beautiful thing about this particular problem is if you look up the change in enthalpies of any element in its natural state or any diatomic element, those are all going to be 0. So the beauty is that everything over here is going to have a zero value, and really the only thing we're going to have to work with is the change in enthalpies of formation of 2 moles of our products. So if you want to know how many moles are in 223 grams of iron, well, you're pretty familiar with having to solve that. So 223 grams, if you look up iron, it's got 55.85 grams per mole. So we're starting with almost 4 moles, 3.99 moles of iron. And if we look up the delta H's of formation, I'll show you what those look like. So have a quick look again at this chart. Like I said, if you have any naturally occurring element like iron, Fe, you're not even going to find Fe any place in our diagram here. You'll find F2, but that's fluorine, that's not iron. And the reason you're not going to find Fe is because unlike the homonuclear diatomics like oxygen, oxygen actually has a value for the change in entropy, but it doesn't have values for change in enthalpy or Gibbs free energy. I'll show you the columns up there. There we go, so you can see. So example would be like iodine. Iodine has a 0 value, even though there's a bond there, but it naturally occurs as I2. So it has no delta H of formation. It's got no delta G of formation, but it does have an enthalpy value. So for our equation, our products are going to be iron oxide, one product, and I'm going to come down here and find that. So iron oxide, our delta H of formation for that is negative 822. And we're going to plug that into our equation. And when we plug it into our equation, remember we just calculated the number of moles. And so our reaction or our equation says the sum of the number of moles of the delta H's of formation of our products. And it was negative 822, but I have 2 of those. So that's each one of those is negative 822. So 2 times negative 822, I come up with 1652. And this is my number of moles, and I'm going to subtract from that my value of the entropies of formation of my reactants. And like I said, neither of these have any numerical value. They're both 0. So 3.99 times a negative 1652, subtract from that 0, and that's going to give me a negative 6,610 kilojoules. So we have calculated the delta H of formation of iron reacting with oxygen to produce iron oxide. All right, hopefully that was a good review for you so that you are comfortable now calculating change in enthalpy, both with calorimetry as well as delta H of formation numbers. Now let's look at some energy diagrams, and then we'll move on to a discussion of Gibbs free energy and enthalpy. All right, here is an energy diagram that I'm going to have you be able, I need you to be able to look at a diagram that's not all labeled. This has everything labeled in it, but I want you to look at one and then to be able to label the different parts. So the way an energy diagram is written, it has a progress of the reaction. In other words, it starts with our reactants and moves to our products. So our reactants are here and we end up at products. But you can see there's stuff that happens in between there. In order for any reaction to happen, you have to break the bonds of your reactants, and there is a certain amount of energy that's required to break those bonds. If you don't have that much energy, then no reaction occurs. And so an energy diagram shows reactants at one level of energy, and we don't have to put a value there, but they have a certain amount of energy, and you have to add a certain amount of energy in order to break the bonds. Once you've done that, then you have an enthalpy change. If it's an exothermic reaction, you end up with your products at a lower energy level, and the difference between this line right there and that line right there is your change in enthalpy. All right, let's look at some diagrams and then have you label them. So this is going to be an endothermic reaction. You notice that your products end at a higher temperature or at a higher energy level than your reactants, which means that you had to absorb energy from your environment to get to your product state. But you still have the same progress of the reaction. You have reactants at one energy level and your products at another energy level. And we have a fairly high activation energy. In order for this reaction to go, you have to add all of that energy, and then once you add it, then you end up with your products at a value of 100 kilojoules. So if we were to label this, we would say this would be our reactants here. This is our activation energy that goes from there all the way from here to there is our activation energy, and our delta H, our change in entropy, is from here, or where we started, up to there. And this one is going to be positive because we have gained in energy. So we have a delta H. We have, let's see if we have all of our things that we're talking about. We have our reactants, we have our products, we've got our activation energy, and we've got our delta H. All right. I think that I'll leave you to do the rest of the energy diagrams. All right, now let's talk about entropy. At least for me, entropy is easier to say and more pleasant to say than enthalpy, so maybe that's brings some joy in this deal. Entropy is a fascinating concept, and it has to be true because we have found that in order for a reaction to be endothermic, the way some of them are, entropy is the only way to explain that. But anyway, we'll come to that in a second. So entropy is a Greek word that means the change within, and it refers to, one way you can talk about it is refers to the amount of disorder in the system. From a different perspective, and the one that's kind of a little more helpful when we talk about thermodynamics, it describes, or it's a measure of the energy that is not available for work. So even though it's wrapped up in the system, you have to subtract this entropy energy out because you can never use it to actually do anything productive. So it can be described as the measure of energy of disorder inherent in the system. There's some laws that go along with thermodynamics, and one of those laws is that the entropy of the universe must either increase or stay the same. It can never decrease. In other words, things are always breaking down and separating. The net total of them are. So I'm going to give you some examples here of predicting. So you can predict an enthalpy change if you just think about whether order is increasing or decreasing in a system. So entropy increases when the products have a greater number of moles of substance. So if you look at a reaction and there are more moles on the product side, so here's a reaction here. We have 1 mole of C6H12O6. But look at all the moles we have over here. I have 2 moles of this and 1 mole of that, so I have more moles of my products than I have over there. Well, that's an indication that entropy is increasing. Also, entropy increases where there's an increase in the number of moles of gas, and that should make sense in particular because gases are far more disordered than solids or liquids. So you're going to look at a reaction and see if you have more gas on one side of the equation or the other. And anytime you have a phase change, if you go from a solid to a liquid, entropy increases. If you go from a liquid to a gas, entropy increases. And it's just the opposite. If you go from a gas to a liquid, entropy is decreasing. And if you go from a liquid to a solid, entropy is decreasing. All right, so here's some examples. Predict the sign of entropy. Is it going to be positive or negative? Is it going to increase or decrease if ice is melting? And this question here is coming to this point here. You have a solid that is going to go to a liquid, and so if solids go to a liquid, entropy increases. And that's just the opposite here. Water freezes, right? We're going from a liquid to a solid, so entropy decreases in that case. Here, as we pointed out, I believe this is a sugar molecule. You have 1 mole of sugar on this side, and you're producing 2 moles of this alcohol on this side and 1 mole of carbon dioxide. And so because you have more moles of things over here, 2 plus 1, as opposed to 1 mole there, entropy increases. Well, look at this one. This one's going to deal with gases. So I have gases on this side that are going to be going to a liquid and an aqueous. All right. So my entropy is going to decrease because I have a higher disorder in my gases and things are more ordered in my products. I have 3 moles of gas on this side and I have 0 moles of gas on that side. So entropy decreases. Let's look at this one. Carbon monoxide gas and water gas. Okay, I have gas and gas. Here I have carbon dioxide and hydrogen, gas and gas. Is there anything that is a change of entropy? Well, my number of moles of things are the same on each side and my gases are the same. So here entropy actually stays the same. Calcium carbonate is going to go from a solid to calcium oxide and it's going to produce carbon dioxide gas. Well, if I have a solid and I'm going to a gas, my entropy increases. So this first part of this entropy deal was just to get you to be able to predict whether your entropy value is going to be positive or negative. All right, let's predict here. If I'm going from carbon disulfide, that's a liquid, to carbon sulfide, that is a gas, carbon disulfide, that's a gas, does my entropy increase or decrease? Well, I'll let you answer that one. If I'm going from 2 moles of mercury and 1 mole of oxygen on this side to 2 moles of mercury oxide on that side, does my entropy increase or decrease? This is a liquid, this is a gas, and I'm going to a solid. And I have 3 moles of things over here and 2 moles of things over there. Those are all your clues about the sign of entropy. And then the last one, I have sodium dioxide, solid. It's going to react with water, and it's going to produce sodium hydroxide and gaseous oxygen. So I am producing gases on this side, so that sure looks like my entropy is increasing, doesn't it? And I'm going from 4 moles of things on this side to 5 moles of things on that side. That also looks like we have entropy increasing. And here's my other thing that's happening. I'm going from a solid to, I don't have any solids over here, so I'm going from a solid to an aqueous solution. So yeah, entropy is increasing there. So that's just all predicting whether it's going to be positive entropy or negative entropy in a reaction. Keep in mind that in the universe, the law says that entropy can never actually decrease the total amount of entropy. But you could have a specific reaction, of course, where entropy is decreasing. All right, we don't leave this just with ideas. We also can calculate some values of entropy. And we use a chart that's very similar and a formula that's almost identical to the formula we used for the change in enthalpy. The only difference is that we are using entropy values. And one other thing you want to note is that these are in joules per kilogram per mole, as opposed to entropy, or enthalpy is usually reported in kilojoules. So this is joules per kilogram. But other than that, we solve it the same way. We're going to take the number of moles of the enthalpies, standard molar enthalpy values of the products minus the sum of the number of moles of the standard enthalpy values of the reactants, and that will give us the change in enthalpy of the reaction. So let's work through this one right here. First thing we're going to have to do is write out the equation. So write out the equation of, you have liquid water being formed from hydrogen and oxygen. So write out that equation, and I'll write out the equation also. All right, so we write out our equation and balance it. It says it's a formation reaction of water, and it says it's a formation reaction of liquid water. That's going to be important to look for the delta S of liquid water rather than gaseous water. And when I write this down, hydrogen plus oxygen, It produces water. I have to balance that, so I have 4 hydrogens on this side, 4 on that side, 2 oxygens and 2 oxygens, so I have a balanced equation. And just like our equation for enthalpies of formation, our entropies have the products minus the reactants, and it also has the number of moles, because each of these values are going to be calculated on the basis of the number of moles of things. So we'll look this up and write out our equation. So we know that our products, there's only one product, water, and it's going to be liquid water. So you notice that liquid water has an entropy value of 69.95, and gaseous water would make sense. It's got more entropy, but we are producing liquid water, so we have to use that 69.95 value in our equation. All right, and when we write down our equation, we want the sum, that's my sum sign right there, and I have 2 moles of my water, because that's here, 2 moles of the water, and my entropy values are 69.95 for 1 mole, so I have to put a 2 there. And I'm going to subtract from that, 2 times 69.95, the sum of my moles of my hydrogen and my oxygen. So my hydrogen has a entropy value of 130.7, and because I have 2 moles of those, I have to multiply that by 2, plus my oxygen, 205.1 is my entropy value, and I only have 1 mole of that, so I have a 1 there. And so I'm just going to multiply 2 times 13.7, or excuse me, 130.7, add to that my 205 and come up with this value, multiply 2 times 69.95 to come up with that value. All right, so when I do my math, 2 times 69.95, I come up with 139.9. I'm going to subtract from that the sum of my 2 times 130.7, I come up with 261.4, plus my 205.1. So this value over here is, add those two together, I get 466.5. And I'm subtracting that, because my equation says I'm subtracting that from my products. So 139.9 minus 466.5 is going to give me a negative 326.6 joules. And at this point, I just want to make sure that this makes sense to me. This is saying that entropy is decreasing because I have a negative value. And does it look like entropy is decreasing? Well, sure enough, I've got 3 moles of gas on this side, no gas on that side at all, and I move from gas to liquid. So yes, entropy decreases in this reaction. Now, the last of our big concepts in this module is that of Gibbs free energy. This is the energy in a system that's actually available to do the work. And Gibbs free energy brings together our change in enthalpy values as well as our change in entropy values. And temperature is going to be a big factor in this. So there are 2 ways that we calculate Gibbs free energy. One is just by calculating the delta H of a reaction and then calculating the delta S of a reaction at a certain temperature, and the delta H minus the temperature times the change in entropy will give me the change in Gibbs free energy. Or the other way to do it is to use the same table just with our Gibbs free energy values in them, and we use the same reaction that we would have, the same formula. The number of moles of the Gibbs free energy of the products minus the number of moles of the Gibbs free energy reactants is going to give me the delta G of the reaction. I shouldn't say that. I should say delta G of the reaction. Yeah. And let me put that in there. There we go. That makes more sense. All right. So we'll calculate the just by once using the values we have of your delta H's and the delta S's, and then we'll turn around and also just use the chart to do it. So let's go back up here. So if we're going to calculate the Gibbs free energy using this formula, we have to know the value of delta H, and we could go through and calculate it just like we have been doing, and we have to know the value of the change in entropy, and we calculated it the way we have been doing it, and you bring those two calculations together, and at a certain temperature, and this temperature always has to be in Kelvin, we can't use it in Celsius, then we can calculate the change in enthalpy, the change in Gibbs free energy. So for an example, in this reaction here, to calculate the delta H, it's pretty easy, again, because our products, our reactants have 0 values for delta H. They're both just natural state elements, and so the only thing we have to include is our delta H of formation of our ammonia gas, and there are 2 moles of that. So if you look up the ammonia gas on a chart, it should come up to 46.2. Let's go to that chart and see if that's true. So I go to my table and I'm looking at my delta H as a formation right here. And you have to look really hard to find them, but sure enough, negative 46.2 kilojoules per mole. And I'll show you that that's kilojoules because it says it's in kilojoules per mole for delta H as a formation. That's my value of my ammonia. So that value goes right there, and 2 moles, so 2 times that. So I have a delta H, a change in enthalpy, of 92.4 kilojoules per mole. I'm going to calculate my change in entropy. Now, these are going to have numerical values. They're not going to have zeros, even though they are homonuclear diatomics. So I've got to find my change in entropy for my product, which is 2 ammonias. So if I look up on that chart, I will find that that is 193, 0.193. Let me go and verify that. And sure enough, I mean, it's written as 193 here, but keep in mind, I have to keep my units consistent. And entropy is reported in joules per mole, and enthalpy and Gibbs free energy are reported in kilojoules. So I'm going to convert my entropy value of 193 joules to kilojoules, and when I do that, I end up with 0.193 kilojoules. And so for that to make more sense, I really should put a 0 in front of that so that we can see that that's what that is. So I have 2 times my 0.193 kilojoules for my ammonia value, and then I'm going to subtract from that my value. I have, let's see, 1 mole of nitrogen gas, so that's my 0.192, and I have 3 moles of my hydrogen gas, that's 0.131. So if I do that math, I end up with 0.199 kilojoules per mole. And then we're just going to plug my delta S value and my delta H value into this formula right here. And so I get my change in Gibbs free energy as being my delta H, which is negative 92.4, that's that right there, minus my temperature. And my temperature, 25 degrees Celsius, is the same thing as 298 degrees Kelvin, and we got to work in Kelvin, times my entropy values, and I come up with a negative 33.1 kilojoules of delta G. Now, the thing that you need to know about delta G is anytime you have a negative value of delta G, that reaction is going to be spontaneous. It's going to occur if you just let it go. Reactions that are positive mean that you're going to have to put in energy to keep them going. But we come up with a delta G value of negative 33.1 kilojoules. So just to recap, the first way we calculate delta G is just to go through the work of first calculating our delta H's and calculating our delta S's, and then making a note of the temperature, and then plugging those values into that equation. The next way to do it is to do something really similar to what we've been doing with our others. We have our Gibbs free energy values in our charts. And so if we want to look those up, we have the formula. It's the sum of the number of the moles of the products minus the sum of the moles of the reactants. And so I'm going to look up our delta G's for my products. subtract from them, add them all together, and delta G's are my reactants, add them together, and I can come up with my change in Gibbs free energy. Now, the good news about the delta G's is that they're like the delta H's. I'm going to have a zero value for my nitrogens and my hydrogens, so they're not even going to be anything difficult to calculate. All I have to do is just look up my change in Gibbs free energy of my ammonia, and that's going to be the only number I'm going to have to deal with. So I have 2 moles of ammonia that I'm producing, and if I look up my change in Gibbs free energy of ammonia, I should find 16.6 kilojoules per mole. Let's look at that and see. So my delta G's of formation are in this column right here. And sure enough, if I scroll down to them, I have a negative 16.6, and delta G's are kilojoules per mole, just like my delta H's, 16.6 for my ammonia. And that's where I get the number to plug into my equation that we're working with. So when I plug that number in, I subtract my delta G's of formation from my reactants from that of my products, and these are 0, and they're 0 again because delta G's are always going to be 0 for any naturally occurring element like iron or whatever it is, plus also the homonuclear diatomics that you guys know about. So I have 2 times negative 16.6. Subtract 0 from that, and I end up with a negative 33.2 kilojoules. And that's not exactly the same number as we calculated up here, but that doesn't matter. We're close. So those are 2 different ways to calculate the delta G's of a reaction. So we can calculate the change in Gibbs free energy of all kinds of reactions. And this is a reaction that we dealt with earlier, iron producing iron oxide. And in that case, the delta G for the reaction, the easy way to do that is to not, calculate the delta H first and the delta S first. Go ahead and just pull these right off the charts. And the beauty of this reaction is our solids, our iron element, that's going to have a 0 delta G. Our oxygen's going to have a 0 delta G. And the only delta G's that we're going to have to deal with are our products here. So we need to deal with the number of moles, and so I have to first figure out how many moles I have in 111.5 grams of iron. So 111.5 grams of iron, and I know that there are 55.845 grams per 1 mole. I have 2 moles of iron if I have 111.5 grams. So I'm going to plug that value, that 2, into here. And so here my delta G for this reaction is going to be 2 times, and then I'm just going to look up my iron oxide value, because both the iron and the oxygen, they are going to have 0 values. So let's look on our chart and see if we can find an iron oxide value and the delta G for it. And when I look on my chart, I come down here, and sure enough, I have iron oxide, Fe2O3, and I have, this is my delta H value. I don't want that. I do want this one. This is my delta G value. And I know I have to scroll up to show you, but this is my delta G column. So the value that I want to put in there is the value of my iron oxide, negative 741. All right, so we're going to plug that value in to our delta G here. 2 times that negative 741 is going to give me a negative 1487 kilojoules, and that negative value shows me that it's a spontaneous reaction, so it will occur, and it incorporates the delta G based on the formations. Well, that's a quick review and a summary of some of the things in this module. I will leave you guys to work through the rest of the problems.